Greetings, friends. Here I am again, almost a month later, able to chat with you again. And my name is John Gabriel, and this is the New Calculus channel. So, if you'll recall, in the past, I talked about how you can form or how you can realize all the arithmetic operations from similar triangles. And now I'm going to slow down a lot and show you how to do that exactly. So let's begin. Now, first of all, how do we realize the concept of a number? Well, we begin with a distance, let's say, or a mass or a volume. And so over here, I have this distance, this red line segment, okay? And how do I even begin to know what it is, right? Until I compare it with something that I do know. For example, something that I might choose to call a unit, or some other line segment that has a common measure with it, right? Okay? So that's the only way you can realize the concept of number, when you begin to compare the quantity or the value with another known quantity which you assume to be the unit. And now this is also true of counting, except in counting we don't really care about the chosen unit, only that it's an abstract unit. So 1, 2, 3, 4, it's still a ratio of two magnitudes, but in this case, the unit is abstract. Okay? So this is how we realize the concept of number, when we begin to compare similar or homogeneous sizes or quantities. So the main proposition in Euclid, which is Book 5 and Proposition 12, basically states the proposition in a way that doesn't mention anything about similar triangles, but it really comes from similar triangles. And what it says is that if you have ratios that are in proportion, like let's say this red segment is in proportion to the blue segment, and this segment here, red segment, is in proportion to this blue segment, then of course if you add them, they will also be in proportion to the totals, right? So this side here will be in proportion to this side here. And as you can see, I have sketched the numerator on the y-axis and the denominator on the x-axis. And 3 divided by 6 is a half, and 1 divided by 2 is a half, and 2 divided by 4 is a half. So it doesn't matter where you are, the ratios will always be the same. So as you can see, 3 divided by 3 is 1, 2 divided by 2 is 1, 1 divided by 1 is 1. Now, this is very important, because when we are about to realize how to do addition and subtraction, and eventually also division and multiplication, we use this exact same process. So I'm going to show you now how it works. So in order to do addition, now let's see here. So on the side here, I've got a numerator of 2, right? And I've got, well, actually the quantities that I'm measuring are 1/2 and 1/3, right? The purple line and the brown line, which contain both two pairs, a numerator and a denominator. So this is 1/2 and this is 1/3, and I want to add them. But because they are not expressed in the same denominations, we need to use this Book 5 and Proposition 12 to make them equal. So, and when we do that, we find that 1/2 is the same as what? What do you think 1/2 is the same as? Think about it a bit. Well, isn't it the same as 3 6s? Right? It is, yes. 3, 3, and 6s. 3 and 6's, right? And 1/3 is the same as 2 6's, 2 6's, right? So once we convert them, then we have these two lines, which we can just take the sum of them, and it gives us the answer, which is 5 6's. I've put an extra value on the side here in case it can be reduced. In this case, 5 and 6 are relatively prime and they cannot be reduced. But if I had something like a half, let's just put a half here, and let's say 2/4. Right, you see, then a half plus 2/4 is really 1, isn't it? So it's 8/8, and these have a common denominator, which is 8, and so the answer is 1. But in any case, this is how you do addition and subtraction, because you simply place the denominator and numerator on the respective axis, and you add them up, and you can see that each time 8 plus 6 will give you 14, which is the green line, and now you have them both in terms of the denomination of 12. Now, an important thing to notice before we can do anything, before we can realize anything about the quotient, is cancellation. And cancellation, again, is made possible by Book 5, Proposition 12, because look, if you have a ratio like this, let's make it like that. Let's say 2/3, or even better, 1/3, and see, so if we have 1/3, that's the same as what? 2 6's, isn't it? So we can cancel out that way, right? And now we're back to a third, yeah? So cancellation also comes from the properties of similar triangles. And I've shown you here how the numerator and denominator are formed. And this doesn't necessarily have to be a right angle, by the way. It can be any pair of similar triangles, provided these axes, or provided the sides are calibrated in equal distances. Okay, and I didn't say unit because you can choose any unit you like. So, and once we've got all these four in place, now we can proceed to define the quotient. Okay, so a quotient, PS over QR, is the rational number that is measured in terms of two numbers, in terms of P over Q and R over S, right? In its most primitive form, it's just simply the ratio of the two magnitudes, which both share a common measure or divisor. So I'm going to show you how to do this with two numbers. And I don't know if you've noticed so far, but I'm showing you how to do all the arithmetic operations simply with addition and subtraction. And of course, addition comes from subtraction, which is the most primitive operator. So we do nothing else but use addition and subtraction and the properties of similar triangles to understand why the operations of fractions work as they do in arithmetic. So P over Q is 4 over 5 and R over 6 is 8 over 10, which means that the quotient will equal to P over Q added to itself n times and R over S added to itself n times, where n is either the denominator Q or the denominator S. And it doesn't matter how you do it, it will always work out to the correct answer, okay? So of course, if you add 4/5 and 8/10, you are going to get 1, all right? I mean, I'm sorry, if you divide, completely wrong. If you divide 4/5 by 8/10, you're going to get 1. Okay, so if you add all these up, you'll see that this is what you'll get. And finally, when you cancel out everything by cancellation, then you'll end up with the answer, which is 1 over 1 or 4 over 4. Okay, and of course, you can do the exact same quotient over here by using n equals 10, right? So add it to itself 10 times and also here 10 times. And so we have found what is the answer of 4/5 divided by 8/10. Okay? Now, that is what is a quotient. And of course, a quotient comes after you've defined addition and subtraction, and addition. And then finally, the product comes from the previous three. So the product of two positive numbers is the quotient of either. Again, you see it's a quotient. I mean, I bet you've never thought of it that way. And this is general. It applies to any number, those numbers that you think of, whole numbers or fractions, whatever. So it's the quotient of either positive number with the reciprocal of the other. And it should come as no surprise that multiplication is defined in terms of division. So let the numbers again be 5 over 6 and 12 over 20. And then what we need to find to evaluate this multiplication is this quotient, okay? And again, we proceed as we did in the previous slide with a quotient with n equals 6, and we see that this this product here results in a half. And I'll leave the alternate method with n equals 20 as an exercise for you. So now, don't worry, I will give you a link to this applet, and you can play with it, and you can come back here and see how the addition and subtraction works. And I will place any other relevant links in the detail section. So, similar triangles and Book 5, Proposition 12, the most important proposition from which we arrive at all the theory of numbers. In other words, we derive the properties of arithmetic from that proposition. Okay, and that's why we know that what we do in arithmetic works, because it works in the geometry that I just showed you, right? Okay, so I hope you've enjoyed this little presentation, and if I'm well enough, you'll hear from me soon. If not, it will probably be another few weeks. So, I hope you'll stay safe, wear a mask, do all that other good stuff. Don't take a chance with the virus. It doesn't matter how strong or healthy you are. I've had bilateral pneumonia, and I can tell you it's a terrible thing. I've had it 5 times already in my life, so my lungs are pretty scarred. And the worst thing that can happen to anyone is not to be able to breathe. And so now I'm taking medications just so that I can breathe and stay alive. Anyway, this is the new Calculus channel. My name is John Gabriel. Till next time, friends, goodbye.